What's up, everybody? This is Mr. Cabilo in the house, and we are going to be talking about the atmosphere today. So you'll need a piece of paper out to jot some stuff down as I go along. I'll have some questions I want you to answer, and I want to take a look at those things tomorrow. Okay? So we're talking about the atmosphere, and the atmosphere is that really thin layer of gases that surrounds the Earth. And it's got a really important role, right? Like it keeps Earth warm. It provides us with air to breathe, kind of important. And it also protects us and other organisms from the harmful effects of the sun, right? That radiation. Now, the atmosphere is composed of a bunch of different gases. Primarily, though, we're talking about nitrogen. About 78% of Earth's atmosphere is nitrogen. And about 21% is oxygen. And then argon's that noble gas that we've talked about before, right? Those noble gases are kind of non-reactive. And then we've got, and that's less than 1%. And then at 0.1%, we have trace gases. So that's all the other stuff. We've talked about ozone before. Many of you have heard about ozone, and you were able to say like, oh yeah, the ozone protects us from the harmful effects of the sun. Well, yeah, it's true, and it's not the main portion of our atmosphere, as many people were surprised, right? And neither is oxygen. So let's look here. If we look, we've got all this other stuff. We're going to be talking a lot about carbon dioxide. So when we say of that 0.1%, most of it's carbon dioxide. Okay, we have neon and helium and methane gases we'll be talking a little bit about. We'll be talking about ozone, but primarily those other gases are composed of carbon dioxide. The nitrogen is the majority, as I said. The nitrogen is kind of, it's not too useful to us as atmospheric nitrogen. We do need bacteria and things like that. The plants use it, but they need bacteria to change it into a usable form of nitrogen. And one misconception is that oxygen is most of our atmosphere. It is not. A lot of people think it's really the majority, and I think it's because it's what we breathe. It's important. And so it gets that extra oomph, but it's really not the majority of our atmosphere, right? The majority of our atmosphere is nitrogen, then oxygen, some argon, and then all these other stuff. And we're going to be focusing primarily on carbon dioxide. Okay. So that's the atmosphere, a mixture of all of those gases, and all of those come together to make up our atmosphere. Now, we are going to talk a little bit about the layers of the atmosphere. I'm not so interested in you being able to label or name the layers. We're going to talk about them in so much as it's important to know the name so that we can talk about it, right? So we're going to use the name so we can reference what we're talking about. But I'm actually more interested in why do we have layers in the first place, right? Why did scientists get together and decide, hey, we should probably distinguish these layers, and what makes them different from all the others? So that's the driving. It's not so much as label them as why can we distinguish between the layers, okay? So the first thing that you should be aware of is, hey, one of the things that happens as we go through the different layers, as we go from Earth out to outer space, is the spacing of the particles changes. They go from really close together or dense to really further apart or less dense. Another thing that happens is air pressure changes. So at different altitudes, meaning as we go from the bottom of the Earth to outer space, the pressure changes. It decreases as the distance from Earth's surface increases, right? Or the further we get away, we have less air pressure. And air pressure, it's really just the measurement of the force which those particles in the atmosphere, all those air particles, are pushing on some area, right? That's what pressure is. So how hard or with what amount of force are those particles pushing on the surface of of the Earth. Okay, so it also depends on the chemical composition. So meaning like what gases or what the atmosphere is actually made of changes in those different layers. And finally, we have temperature. And the temperature is actually what the scientists are going to use to divide the atmosphere into 4 different layers. Sometimes we talk about 5, the ionosphere, but we're going to talk about 4 because the ionosphere is really part of 1. So these are the 4 layers. We have the troposphere. This is actually the layer where we live. The troposphere is the thickest layer, and it provides the oxygen that we need. What we're going to talk about later, the troposphere is where weather takes place. So we're going to be talking about weather and climate, and really all that's taking place within our troposphere. So this is the really important layer that we're going to be focusing on. It is the most massive. It's actually 90% of the total mass of the atmosphere. The air here is denser than it is in all the other layers of the atmosphere. So those gas molecules are really close together because Earth's gravity is greatest near Earth's surface. The temperature here, and that's what this red line is indicating over here. It's indicating the relative average temperature of those layers. So the temperature of the troposphere is greatest near Earth's surface. So you can see here, hey, closest to the surface, it's on average, these are just estimates, of 20 degrees Celsius. And as you can see here, the further we get up, the higher away from Earth's surface we get, or the further away we get from Earth's surface, the cooler it is. That's what that's showing. So the trend in the troposphere is temperature is decreasing as we get up, as we go up away from Earth's surface. So you can see here that because of that, the change in the temperature is going to result in some mixing. So as things warm and cool, we're going to mix gases. And so the overall chemical composition, or what gases we can find in certain places, are fairly uniform. It's constantly stirring those gases in the troposphere, which is pretty cool. So as you know, air expands and rises, and then it cools and becomes more dense. We're circulating the air, right? So it heats and rises and becomes less dense. Then it cools and sinks and becomes more dense, and we continue to circle the air or the gases in the troposphere. So they're nice and mixed here. We do get a lot of water vapor here, and it does vary. So you can imagine that the water vapor may be above the ocean right here, might be a little bit less over here. Okay, so there is water vapor in the troposphere. How much depends on when and where. Okay, and we'll talk about pollutants later. The amount of pollutants in the troposphere also depends. Okay, so next layer we have is the stratosphere. Now we can see where the troposphere ends and the stratosphere begins by looking for where the air is cooling and sinking. So at the top of the troposphere, we're going to reach a boundary where the air is sinking back to the surface. So it's no longer cooling. The temperature has, it stopped decreasing. Cool air sinking back towards the surface. That's going to be our boundary where we're going to start entering the stratosphere. Okay, and we can see that also with the temperature change. And we have seen, or you can look up and see a different image here. The change in temperature is a little bit less dramatic on this image than some other images that I've seen. It's a lot more defined, and that might just be based on the way that this is scrunched over here in the corner. But we can see that as we go up in the stratosphere, the temperature is changing. So as you go up in the stratosphere, temperature is starting to increase. if you can see here, we've started, this is saying it's negative 60, and to the top of the troposphere, we're looking at, I don't know, what does that say, 0, right? But it's gone up. That's a significant change, right? 60 degrees Celsius change, according to this image here. So we can see a few things. We can see the temperature change, and we can see that in the stratosphere, we actually are going to have very little water vapor. So we're not going to see a lot of clouds in the stratosphere because clouds are made up of water vapor. So no clouds here, or very few, because of the lack of that water vapor. The chemical composition here, we're not going to get a lot of mixing because that warmer air is located above the cooler air. So it's not going to, like in the troposphere, where it was warmer down here, so it rose up to the top, right? It became less dense, and then it cooled and sank, and we had this continual cycle. It's warmer up here in the stratosphere. Okay, so we don't really, it's already less dense to more dense, and it's going to stay that way. And so we're not going to get a cycling, and so the chemical composition, it depends on the altitude. So if we look at the top, we're going to see different gases in the stratosphere than if we look at the bottom. And one of the gases that we can notice is the ozone. So we have the ozone layer, which is, the ozone is 3 oxygens bonded together. And this is that layer that protects Earth by absorbing all that ultraviolet radiation from the sun. Okay? And the air here in the stratosphere is warmed by the absorbed radiation. So temperature in this layer increases as the altitude goes up. Speaking about ozone, this is probably a good time to mention that the ozone layer is necessary for life. But there is good ozone and there is bad ozone. So ozone can be broken up into ground level ozone and ozone that's up in our atmosphere. Ground level ozone is bad ozone. It's the harmful ozone, and the reason it's harmful is because it is pollutant, really. It's produced when sunlight reacts with vehicle exhaust and some oxygen in the air, or basically pollution and oxygen in the air. And sometimes people say ozone action days, and that's like, hey, you should limit your outdoor activities because ozone can damage your lungs. We probably don't hear a lot about that in Ohio, but you can focus in on some things like that. So just keep in mind, there is a harmful and a beneficial or good ozone as well. And I'm going to show you a video later, and he's going to mention that, so I wanted to mention that here as well. Okay, next we have the mesosphere. Now, the mesosphere temperature is starting to change pretty dramatically. So you can see here as we go up in the mesosphere, temperature is decreasing. So why is that? Why is temperature decreasing in the mesosphere? Well, it's because it does not have an ozone layer. It can't absorb the ultraviolet or that UV radiation, and it therefore can't warm the air. So as we get away from that ozone layer, temperature is decreasing, or as altitude goes up, temperature goes down. The lower mesosphere is warmed up by the stratosphere. So the top of the mesosphere will be the coldest part of the atmosphere. It is actually, it's kind of a hard layer to study or to look at. That's because it's really higher than aircraft can fly, and lower than satellites orbit. So it's in that kind of like dead zone, basically. But we do know a few things here about the mesosphere. It is breaking up those the meteors that are going to come here, so it is a nice protective layer. With the ones that enter our atmosphere, those are protected or broken up as they go through the mesosphere. Okay, so the next layer we have is the thermosphere, and this is the upper layer of the atmosphere. We're at now like 80 kilometers above the surface. So this is kind of an interesting layer because the air temperature stops decreasing here, as you can see, and it starts to warm up, which might be counterintuitive. So why is it doing that? Well, here it's a little bit different. So remember, temperature has to do with how the particles are colliding with one another. That's how we're going to transfer thermal energy, is through the collision of particles. But in the thermosphere, the particles are really far apart, so they're not colliding, or they're rarely colliding, I should say. And therefore, very little transfer of thermal energy happening in the thermosphere. But what is happening is solar radiation is actually breaking apart molecules. So that, remember, we have nitrogen and oxygen primarily. And so we're going to split the nitrogen and split the oxygen into atomic nitrogen and atomic oxygen. So just one O or one N, just one of those particles. And so what that means is, well, that single oxygen is really good at absorbing solar radiation. And so because it's really good at absorbing solar radiation, the temperature is going to be higher all the way up here in the thermosphere. So temperatures at the top are going to be high because it has a lot of that atomic oxygen. But what's also interesting is, because those particles would rarely collide with you, if you were in the thermosphere, it wouldn't really feel very hot, because there's no way to transfer that energy to you through collisions, because there's so few of them. So pretty cool. All right, so now I want to talk for a minute about weather in the atmosphere. So I mentioned that the weather that we're going to experience is happening in which layer? That would be the troposphere, right? So all the weather's happening in the troposphere, and that's because of that's where the water is, and remember, we're going to get rain or snow or ice from that water vapor in the troposphere. And to talk a little bit more about how weather and climate are related, we're going to jump over to a quick video.
The atmosphere surrounds the Earth. Scientists break it into a number of different spheres. We've got the tropostrato, meso, thermo, and exosphere. Now, we live in the troposphere, and that protective ozone is going to be found right at this boundary between the two. Weather is going to be the current state of our atmosphere, and over a long period of time, we call that climate, which is due to the tilt of our axis and where we are in the orbit around the sun. And so due to our location, we get seasons. We're pointed towards the sun in the summer and away from the sun in the winter. But also, since we're a sphere, we're starting to get unequal heating of the planet, and those convection currents lead to cells in the atmosphere. Got things like the Hadley cell, the Ferrel cell, and what those are doing is moving the atmosphere around on our planet. Now, we also have a spinning planet, and that creates something called the Coriolis effect, and so it spins in a characteristic way. And so the combination of these two lead to atmospheric circulation. It's moving the weather around on our planet. Now, the oceans also affect our climate. And as the atmosphere moves around, it starts to move the oceans. And so we get these ocean currents, which are shaping our climate. And an example of all these things coming together is El Nino, or ENSO, the El Nino Southern Oscillation, which we'll talk about in a little bit.
So you don't need to know all that in that great detail, but I really like that he put together this graphic, right, that talks about how weather is our day-to-day, or what's happening in the atmosphere right now, and our climate is over a long period of time, all that on weather on average starts to make up our climate. And then he goes through and talks about some of the things that we might experience or that influence that as well. All right, so I think this is a good time to have a little bit of a review. So on that piece of paper I asked you to get out at the beginning of the video, and if you've been taking notes on that piece of paper, this is a fine place to answer them as well. Just make sure I can see them different from your notes. So 3 questions. So go ahead, you can answer question number 1 is I want you to write down what the composition of our atmosphere is. I'm looking for what are the gases that primarily make up our atmosphere. Question number 2, and you can pause the video obviously if you need more time. So question number 2 is just true or false, air pressure increases closer to Earth's surface. So generally as we get closer to Earth's surface, is air pressure increasing? True or false? And number 3, the atmosphere is a mixture of gases that surrounds a planet or a moon. True or false? Okay. Go ahead, if you haven't answered those already, do that now, and you can pause the video. I'm going to continue on. Okay, so now we're going to jump back to my good friend here for a nice video overview of what we've already talked about, and he'll add it in a couple details as well.
And so the atmosphere is a series of spheres that surround our planet. This is not to scale, but the lowest one's going to be the troposphere. That's where our mountains are. That's where we are. When you're on a jet, you're still within the troposphere. Above that, we're going to have the stratosphere, so weather balloons will move into that area. If we look at ozone right here, so this is going to be ozone right at the surface of the planet. We're going to have some bad ozone. We call that tropospheric or smog ozone that can be damaging to us. We'll talk about that later. But as we move up in the troposphere into the stratosphere, we're going to have a huge increase in that ozone layer. That's that protective layer around us. Above the stratosphere, we have the mesosphere. That's where meteors are burning up. Above that, we have where the aurora are. That's going to be the thermosphere. And then finally, we're bordering space. This is going to be the exosphere up here. Now, what are some conditions within the whole atmosphere? We're going to increase density the closer we get to the Earth because there's higher gravitational pull the closer we are. Now, what's the atmosphere like today? That's weather. Raining, is it sunny, what's the temperature? And that's important. But what's more important is climate. That's going to be weather over a long period of time. And if we look at this biome map, you start to see some patterns. And so if you look right here, we're going to have a bunch of tropical rainforests. We'll have deserts right here. And if I put the latitudes over this, the one thing I'm always surprised is how low the equator is. So if we put this in at 0 degrees, then 30, and then 60, real patterns start to emerge. So right here along the equator, we're going to have all of this precipitation. Rainforests are going to be found there. But look, right here at 30 degrees above and below, or northern and southern, we're going to have these deserts. And then we're going to have these big boreal forests out here. And so all of that has to do with where the Earth is in orbit and also the tilt of the Earth.
All right, so that was good review. What I want you to do next on your piece of paper is go ahead and draw a model of those layers. We just saw the dude over there go through his model. And I want you to include the 4 layers that we've talked about: troposphere, strato, meso, and thermosphere. And then I want you to just in that diagram, in that model, include a few characteristics of each of those layers. You can use your book if you want. You can use the notes. You can go back in the video, whatever sources you want. Okay, but I want to know, what's going on? What are some characteristics? Where's the ozone layer? Where might I find spaceships or airplanes or whatever? And I should include this on here. I also want you to include temperature, right? That's the temp, if I can spell temperature, because that's what scientists are using to distinguish between these layers, is the temperature, right? So I want you to include what's happening to the temperature in each of those layers. Okay, go ahead and do that now. All right, so now that you have that done, let's talk a little bit more about temperature. The main thing of the atmosphere is that temperature on Earth would not be stable without our atmosphere. So we need that atmosphere to keep us warm. And without it, it would be way too cold for life. We would be freezing. Nobody would be able to, no life as we know it would be able to exist on Earth. And so we are really thankful for our atmosphere, and we're really thankful, at least to some degree, for an effect called the greenhouse effect. So what is the greenhouse effect? Why does it keep us warm? And to answer some of those questions, I'm going to turn back to another video. And we're going to see what they have to say.
The Earth and the Moon are basically the same distance from the Sun, yet temperatures on the Moon average an unlivable -18 degrees Celsius. And even deadlier, they range from -170 Celsius during lunar night to 100 Celsius at lunar noon, regularly exceeding both the coldest and hottest temperatures ever recorded on Earth. And while the days and nights on the Moon are about 14 times longer than those on Earth, our planet's relatively fast rotation isn't what spares us from those loony temperatures. What protects us is our atmosphere. By day, it serves as a shield, blocking out the most harmful and energetic of the sun's rays and about 1/3 of the less intense but visible light. At the same time, it traps the infrared radiation, aka heat, radiating out from Earth's sun-warmed surface, keeping us from freezing solid at night. In order for our atmosphere to absorb any kind of radiation, it needs to have some electrically charged particles for passing electromagnetic waves to push around. And most of our atmosphere is made up of gas molecules that don't have an electric charge. They all have a balanced number of positive protons and negative electrons. But some molecules hold most of their negatively charged electrons closer to one side, lending them a lopsidedness that can jiggle back and forth to absorb the energy of incoming infrared rays. For example, water, ozone, and nitrous oxide are all electrically lopsided, so they all absorb infrared radiation. Then there are gases like carbon dioxide and methane. On paper, neither molecule looks lopsided, so it doesn't seem like they should be able to absorb any radiating heat. But in reality, gas molecules aren't motionless. They crash into each other billions of times per second, knocking each other in different directions and also into different modes of rotation and vibration. And it turns out that both carbon dioxide and methane spend most of their time shaking it in electrically lopsided ways, allowing them to absorb infrared rays and help insulate the Earth. Even though many different kinds of molecules can absorb infrared radiation, the vast majority of our atmosphere can't, because it's made of nitrogen and oxygen, which don't get lopsided even when they are vibrating. They're too symmetric. Nevertheless, the lopsided 1% are such good infrared absorbers that they manage to intercept about 90% of Earth's outgoing heat. Each captured ray gets pinged around the atmosphere, and most end up returning to the surface at least once before escaping to space. We don't need to visit the moon during frigid lunar night to know just how important the game of radiation pinball is for Earth. Ice records from our own coldest climate show that small natural variations in atmospheric carbon dioxide produce relatively big changes in temperature. They also show that, compared to the last 800,000 years, the game today is much, much harder.
Okay, so what were they talking about in that video? Well, they were making some like crazy Tay-Tay-Swift references about particles shaking it off, and what they're really getting at is that those particles are sending back or shaking their configuration so that they can absorb or give back infrared radiation, also known as heat. Basically, to sum up that whole video, what they're talking about is our atmosphere has some gases that send, and those gases are like water vapor, and they're like carbon dioxide. They also talked about methane and a couple other ones. We're going to focus primarily on carbon dioxide for right now. And what they're doing is they absorb and they send back the infrared radiation from the sun, much like, and this is where it gets its name, much like a greenhouse would for when they grow plants. That's how it can be. In the dead of winter, it can be really warm. You can grow tomatoes in a greenhouse because glass has the same sort of effect. Yeah, so glass can allow the infrared radiation, which is heat, allow the infrared radiation to go through the glass and then not allow it to escape. So it would bounce around in here, trapping all the heat or the infrared radiation, so it's really warm in here while it's super cold out here. And that's exactly what our atmosphere, it's like a blanket, or like we're surrounded in a glass layer, not a glass ceiling, okay? Like a glass layer that is trapping heat because it's bouncing off of those molecules. And we saw in the video carbon dioxide and water vapor were some examples. So now I want you to just imagine, okay, so we've got these particles or these molecules like carbon dioxide in our atmosphere, and infrared radiation is bouncing off of them, trapping our heat. So I want you to think about that, and I want you to answer this next question, okay? The question is, what would happen, do you think, if we changed the concentration or the amount of those greenhouse gases in the atmosphere? Okay, so could be any of them, right? I've said we're going to focus on carbon dioxide, so you can substitute that if you want. It could be water vapor, it could be methane, but what do you think would happen if we change the concentration or the amount of those greenhouse gases in the atmosphere? Meaning if we got more of those, or if we got less of them, either way, your take, what would happen in the atmosphere? So a few minutes to answer that. Okay, so that's it. Please make sure that you bring your questions in tomorrow. If you have notes on them as well, remember, that's fine. I'm going to just look at it and give it back to you. But that's it. All right, thanks for watching. I'll see y'all tomorrow.
Got nothing in my brain. That's what people say. That's what people say.